All right, so now knowing what we know, what is the ideal separation? Well, I think you can probably state that you want something that's fast. You don't want something that's going to take you um, 10 hours to do one sample of separation. But you want that to be counterbalanced against the sort of opposing metric that we mentioned with resolution. So you want it to be fast enough that you don't have to wait forever, but you still have adequate resolution between your key analytes, whatever you're measuring. But you don't need to be overkill, right? You don't need to go overkill in either direction in terms of the speed or resolution. You just need it to be good enough for the methodology that you need in place. The other thing we haven't talked about, but just in terms of the fate of the field of separations, we want to do these things in a way that's efficient from a resource perspective and a time perspective. So we want to use a minimum amount of solvent. We don't want to have to do separations on big scales where we're using gallons of solvent to separate things out. So those are sort of the two big metrics nowadays that are motivating the field of separations, aside from just more and more exotic separations and different methodologies. As a total aside, I'll say that both of these things are fixed largely by this thing called miniaturization. And we're not going to talk about that in this class, but this is one of the biggest components of modern analytical chemistry. How do we build these things called lab on a chip? These tools that allow for separation and detection on a micro scale using things like microfluidics, which is the focus of some of the research that I do in my lab. And in the case of separations, miniaturizing your separation, doing it on a really small scale is cool. It's pretty neat to be able to do, but as you can imagine, it uses much less solvent. And sometimes we're talking about like single microliters. It's usually much faster because we're doing separations over tiny distances. And sort of implicit in this is it uses less of our sample, and so it's less destructive. If we have precious amounts of things, maybe we're trying to separate neurotransmitters from cerebrospinal fluid that's extracted from a mouse brain under a certain stimulus. You don't have much of that, and once you use it up, it's gone. It's not easy to get again, in which case doing this on small scales is really powerful. And with the advent of a lot of the techniques that we have for microfabrication and the construction of small tools, it's really exploded this field. That's not the focus of this video, but I wanted to give you a framing of that. If you go on and take Chem 342 with me, we will talk about miniaturization. You'll build your own lab on a chip devices in my class, and then you'll assess their metrics for separation and detection. So the thing always working against us in a separation, if we're thinking about our ideal separations, whether it's on the macro scale or the tiny scale, the miniature scale, is this thing called band broadening. And we talked about its origin in this sort of random 1D walk expression and its similarity to binomial distributions or Gaussian type normal distributions. But I want to expand upon this a little bit more because there's a lot of things that contributed to broadening, and so those things impact how we should think about constructing our separation, what makes for a good separation. So band broadening, we talked about the proxy. We use either sigma, which is the standard deviation of the band because it's a normal distribution, or we square that and we get the variance. So here I'm just talking about the variance, which is, again, it's just a quantitative proxy for the width of a band at any given moment in time or distance from the point of injection. And we have what we observe. If we've got a band and it's, we measure it, literally we measure it on a chromatogram, we have whatever the actual standard deviation squared of that distribution is, of molecules in space. But that distribution is going to be a summation of several different components that we can think about. So the total observed broadening is just going to be a summation of lots of different inputs, different things that lead up to this. And so isolating and minimizing these things, several of them are working against each other, so there's no such thing as just minimizing everything. But identifying sources and minimizing them will decrease our overall band broadening, which again serves to increase the total number of plates that we have, which increases the resolving power, which increases the efficiency of your separation, which is what we're all striving for. So the first thing to consider is the injection volume, and I alluded to this previously, right? If you could insert an infinitely small amount of your mixture onto the column, then you're minimizing the concentration, and you're also minimizing the width of the band to start with, right? If we've got a column and you insert this massive plug of sample that's this wide and it's purely concentrated, your starting point for Fick's law of diffusion is already in a bad place. This thing's going to diffuse both rapidly, the flux is going to be high, and it's going to diffuse far. So your distribution is going to be really wide like that. But if you oppose this to, say, an infinitely small band, which is this orange line here, then we're starting at a really, really narrow starting point, which doesn't mean it's not going to broaden out. It just means by the time it gets to the end here, x of the total length of your column, it's going to be less broadened. So injection volume is a huge one, and you'll see a lot of techniques that we utilize try to minimize injection volume to like microliters on the order of 1 or 2. And if you go down to the microscale separations, like lab on a chip, you can be separating things on the nanoliter scale, or sometimes even smaller. The opposing side of this is the detection volume, because if we were able to insert an infinitely small injection volume, or even just a practically tiny injection volume, that might mean that by the time this thing actually does spread out down here, we don't have very many molecules at any given moment in time to actually detect it. Maybe it'll be below the detection limit of what we're trying to measure. So we're sort of constrained in terms of our injection volume by some minimum based on the detection scheme that we employ. So these two things are intimately related, where we have to have a minimum injection volume to have a reasonable detection volume, but we want to minimize the injection volume to minimize this contribution, this parameter to the broadening effect. Another thing we talk about is laminar flow. So when we're talking about the flow of fluid through a small tube, we can have generally 2 large classes of flow types, although I'm far oversimplifying that. I'm not a fluid mechanics guy. But as things move, you sort of have this general structure where you end up having almost a meniscus, like a bead that flows, where you have sort of the tip of the spear as this thing moves, where really you have like all of the different parts of the fluid are moving in perfectly parallel lines at an infinitely small scale. That's what's laminar instead of turbulent flow. And what that does is, as you can imagine, if you've got a detector right here, whatever that is, it sees this point first and this point last, and depending on how pronounced those 2 points are, that leads to an implicit distribution just simply based on what we're detecting. That may have nothing to do with the issues with simply fixed diffusion. This is purely a fluid flow dynamics issue, which can lead to this. So laminar flow is a consideration that we need to consider often, especially in small devices where laminar flow is more pronounced. So we also have longitudinal diffusion, which is exactly what we were talking about with Fick's law. This is just saying that if there's a concentration gradient, which there almost always is if you're trying to separate something, you will have diffusion, but you'll have it isotropically, meaning even though the fluid flow is net from left to right, it doesn't mean that the Fick's law sees any of that. There's going to be a diffusion isotropically in all 3 dimensions. We are sort of approximating this as one-dimensional. And that leads to just band bending simply because of diffusion. Of course, in this case, what could we do to mitigate longitudinal diffusion? Well, we do this faster. It means the faster we can separate this thing, then we minimize the time that we allow for longitudinal diffusion to occur. If we can do a separation in 1 second after the injection occurs, then at that point there's been almost no time for the random walk to occur, for these particles to actually move next to each other and start to diffuse outward. So you're working, sort of in opposing forces, because if you try to increase the speed of your separation to minimize longitudinal diffusion, then in small devices you're maximizing laminar flow, which is going to just increase, its broadening contribution from that component. And so, this is sort of an optimization problem where you have lots of variable inputs. And remember, we're not necessarily trying to overall minimize find the lowest possible broadening for a particular species. We're just trying to do it well enough that we can get resolution on our chromatogram. We can actually detect distinct features of what we're trying to separate from our mixture. Last one I'll mention is one that's not necessarily intuitive, but it makes a lot of sense when you think about it, and that's this component called mass transfer. So this gets back to this notion of what a theoretical plate height is, and that, as we talked about, was approximately the length of the column that our species that we're trying to separate can equilibrate with the stationary phase. So that means it's actually, whatever the mechanism of interaction is, it is based on some equilibrium constant, some interaction, whether that's absorption based on charge or size or whatever. There's some equilibrium that's established, which means there's some time to reach equilibrium. And if you're talking about something moving at a rate of u sub x, right, then that rate could be equated simply to a distance. So how far on the column does this thing have to move to reach one equilibration cycle, which we call this h, the theoretical plate height. But now if we think about that, what's happening is there's a distribution of the molecules and when they adsorb and when they desorb. And so if this is your original band, this plug, which is sort of, I've got it crafted like laminar flow here, right? This thing is maybe still adsorbed into the stationary phase layer, and the plug is moving past it, right? The plug is just chugging along, and it's broadening, but the way it's broadening due to mass transfer in this case is that A is sticking around longer when it's bound here than it is here, which means this A probably isn't contributing to the broadening, but A that's right at the end, on the slow end of our plug, is going to slowly, because the plug is going to move away faster than A can desorb out. And so what you end up with is a plug that keeps getting wider and wider as you go further and further, just because simply the time it takes for A to come back out of whatever the stationary phase that it's bound to. So that's the mass transfer contribution to broadening in this case. So all of that brings us to this new and other hypothetical expression called the Van Deemter equation, which relates, again, this is not a quantitative metric, this is just simply for us to functionally relate the impacts of certain broadening effects on the theoretical plate height. So H here being the theoretical plate height. And as it's sort of impacted by three key components, A, B, and C, and Ux here is velocity. So it's implicit, that velocity or the flow rate of the system, and how that impacts these three parameters. So parameter A is this thing that we call eddy diffusion, or some people call eddy diffusion. Your book or other places may call this multiple paths. And this is a pretty simple one to describe, which just says it's a function of how you pack your column. And so you've got this band that you insert, which is on the far left, and then it's just showing you three possible paths that any component inside that band could have taken and will have taken. And what it shows is that if you have lots of different path options, then we will have broadening simply implicit, because this thing, through the random walk, will have to move further in some paths and move less far from the central axis than others. And that just reports on how much broadening is simply based on the diffusion, the eddy diffusion, or the option of taking multiple paths. We call that we denote that with this parameter A. And note that the parameter A here is independent of flow rate. There's no UX parameter affixed to this, and it makes sense, right? the length is not going to be impacted by how fast it's moving. It's still going to have multiple paths. One thing that we could do, though, with multiple paths is just to decrease the particle size. Right? If you decrease the particle size, then there's less then these particles have less far away to move away from the central axis. So decreasing particle size could decrease this component A, which then in turn decreases our theoretical plate height, which of course increases our plate number, which of course increases our resolving power, our separation efficiency. Parameter B here, this is just the standard old longitudinal diffusion. This is fixed diffusion that we're used to. So you can see that that's inversely proportional with our flow rate. So if we can crank up the flow rate of the system, then that decreases the time that our band is sitting on the column, which means that we have less contribution to our theoretical plate height from longitudinal diffusion. And then the last one here is mass transport, which I just defined in the previous frame, where you have some equilibration cycle between different components, and so you sort of have two different time frames, time 1 here and time 2 here, and they're showing 3 different compounds and that equilibration time and how long it takes to get there. Here they're showing you, you've got point 1 or particle 1, 2, and 3, and those are just further away from the stationary phase, and in this case the phase is sort of on the outer walls. And so the equilibration time is different for all 3 of these particles, which leads to this sort of plug broadening out over time. And you can see that that is linearly affected by the flow rate. And so just as the flow rate in this case serves to mitigate the effects of longitudinal diffusion, in the case of mass transport, the flow rate of the system actually further exacerbates its effect. Because as you can imagine, if the mobile phase starts cruising through here at much faster rate, that's even less time for all 3 of these particles to re-equilibrate, which further exacerbates the broadening contribution from that. And so the Van Deemter equation is just a sort of simple way to look at the 3 major primary inputs into what impacts the separation efficiency, in this case approximated by the theoretical plate height on the column. So plotting the Van Deemter equation, or plotting each of these components, is what we call Van Deemter analysis. And what you can see is that we have the plate height, so h here, is on our y-axis, so that is h here, as a function of ux, the flow rate of the system. And what we see are 3 plotted lines here, one for each of the individual components A, B, and C. So if we look at, say, the multiple paths component A, you can see that as just this straight line because it's independent of the velocity of the flow, whereas the longitudinal diffusion component decays as 1 over u, so we get this sort of effect, and then finally we have this linear mass transport contribution, so we get this sort of straight line going up as a function of flow rate. And the optimization or the minimization of the plate height can be found by plotting the composite here, which is the blue line, which is the actual full Van Deemter. And so what this allows us to do is sort of experimentally optimize what our flow rate should be to get the maximum separation efficiency for a given analyte. So you can imagine if you wanted to produce a Van Deemter plot like this, which people don't often do in the full sense because you can get a pretty good sense without having to make a full plot, but if you wanted to, you could compute experimentally the theoretical plate height by experimentally determining n, which I showed you in a previous video how you could get the theoretical number of plates for a system and you could measure the length of the column, so that means you'd extract h, so you'd be able to measure the plate height and then do that at several different flow velocities of the system. You wouldn't be measuring each one of those contributing values, but you'd be measuring the blue curve. And the blue curve then would tell you wherever that's at a minimum, that's going to give you the best separation efficiency, the highest resolution, and the minimum plate height for that particular analyte. So there's several different column geometries, and we're not going to be exhaustive at all. This was really the focus of like a graduate level separations course to really go into the details here. But in a general sense, there's a sort of a continuum of different column interiors. You either have the packed column, which we've talked a lot about, or at least implicitly I've showed you a lot of the examples, where you just have a bunch of beads and then you functionalize the surface of those beads with whatever chemistry is intentional in terms of the separation that you want to run. Those can be either porous, or they can be meaning they're actually porous, means you have a higher surface area, or they can be solid beads, so they're like glass beads versus like some porous polymer layer. And then you have the opposite of this on the spectrum, which is what we call the open tube or the capillary type column, which I also showed you some examples implicitly. And in that case, instead of having an entire thick packed column, you end up having a really thin column on the order of like hundreds of microns, so like maybe a few hairs width thick, but you know, that would be impractical to pack with stuff. But what you can do is just functionalize the outer wall of the open tube with a porous or an actual solid layer, and in that case, because the diameter of this capillary tube is so small, any particle, even in the centroid, doesn't have far to diffuse. And so this works pretty effectively too. The good part about capillary tubes is then they can be super long. And so as we talk about gas chromatography, I'll show you a capillary column that's 30 to 50 meters, so we're talking about 150-ish feet long that we're separating gases over in this sort of open tube capillary, whereas like a UPLC column that we use on the ultra high pressure liquid chromatography system may be on the order of less than 10 centimeters long, but its diameter is on the order of like 1 centimeter as opposed to tens or hundreds of microns. So just sort of think hypothetically in this Van Deemter equation, what the contributions to plate height are as a function of these different columns, and we won't consider this last one here. But for packed columns, all three terms are operative here. Certainly multiple paths is a big one, which is going to be a function of both the size of these beads and also their porosity. Um, Longitudinal diffusion is going to be important in terms of its length and how fast things can move through this, right? If it's a really tightly packed column, then things may move slowly through there, which then is going to negatively impact the longitudinal diffusion component here. And then in terms of C, just depending on the surface area of these particles, that's going to dictate how far a molecule or species has to move along the length of the column to go through one equilibration cycle. So decreasing that makes decreasing the particle size decreases the contribution for mass transport in this case. If we have open tubular columns, in that case you pretty much eliminate the multiple paths problem because there aren't multiple paths. You essentially have laminar flow through the system, and so everything is on nominally a similar path, and it's so narrow there aren't that many, it's not a very wide thing where a molecule can diffuse far from the centroid out. In that case, then we're just thinking about longitudinal diffusion and mass transport, and we won't consider capillary electrophoresis because we're not talking about that in this chapter.